My name is Antoine. I'm a PhD student at the University of Massachusetts Amherst. I am presenting our paper, KinyaBERT, a morphology-aware Kinyarwanda language model. Today, I'll talk about the motivation for this research, then present KinyaBERT model architecture in detail. I'll then talk about our experimental results, then finish with some conclusions. We all know that recent natural language processing advances have been made possible by the use of pre-trained language models such as BERT. However, there are still a number of limitations. Due to the complex morphology that is expressed by most morphologically rich languages, the ubiquitous byte-pair encoding tokenization algorithms that are used cannot extract the exact subword lexical units, meaning the morphemes, which are needed for effective representation. For example, here we have 3 Kinyarwanda words that have several morphemes in them, but the BP algorithms cannot extract them. This is because some morphological rules produce different surface forms that hide the exact lexical information, and BPE, which is solely based on the surface forms, does not have access to this lexical model. The second challenge is that even if one had access to an Oracle morphological analyzer, replacing BPE tokens with morphemes is not enough to express the morphological compositionality. A third gap in research is that new pre-trained language models are most often evaluated on high-resource languages, and we need to assess their applicability on low-resource and diverse languages as well. Therefore, we present KinyaBERT, which is a simple but effective adaptation of the BERT architecture that is meant to more effectively handle morphologically rich languages. We evaluate KinyaBERT on Kinyarwanda, a low-resource morphologically rich language which is spoken by more than 12 million people across Eastern and Central Africa. The input to the model is either a sentence or a document. For example, here we have John twarahamubonye biradutangaza, which means we were surprised to find John there. As you can see, Kinyarwanda words contain several morphemes that contain different information in them. Therefore, in our model, we pass this sentence or a document to a morphological analyzer, which then generates morphemes contained in each of the words. The morphemes usually are made of a stem and 0 or more affixes. The affixes may indicate tense, aspect, subject, or objects in verbs, and more often relate to the Bantu noun class for subjects and objects. The morphological analyzer also produces a part of speech tag for each of the words. After this step, we make embeddings for the part of speech tags, embeddings for the affixes, and embeddings for the stem. These are the morphology level embeddings. We then pass these embeddings through a morphology encoder, which is a small transformer encoder that is applied to each word independently. The output are the vectors that are contextualized with the morphological information at each word. Now we perform composition, where the morphological embeddings corresponding to part of speech and stem are concatenated together. We further concatenate them with another stem embedding at the sentence level. Then we form an input to the main sentence or document encoder. The final output are contextualized embeddings that can be used for downstream NLP tasks. For our morphological analyzer, we use finite state two-level morphology principles with custom implementation that is tailored to the Kinyarwanda language. We effectively model the morphology of all Kinyarwanda words, including verbals, nouns, demonstrative and possessive pronouns, numerals, and others. We use an unsupervised part-of-speech tagging algorithm. A first-order factored model is used to account for morphology probability, basically the probability that is assigned by the morphological analyzer. We also take into consideration the part-of-speech tag precedence as well as the syntactic agreements that are present in the input words. The part-of-speech tagger uses a bidirectional inference, which improves upon the more often used Viterbi algorithm for decoding. A few remarks here for positional encoding. 1. The morphology encoder does not use any positional encoding. This is because each of the morphemes occupies a known slot in the morphological model. Therefore, positional information is inherent when the morphemes are given. Second, the sentence encoder uses the so-called untied relative positional embeddings, which have been recently published at iClear conference. These positional embeddings essentially disentangles positional correlations from token-to-token attention computation. Similar to BERT, we use a masked language model pre-training objective. Essentially, we have to predict both the stem and the affixes that are associated with the words. During pre-training, 15% of all words are considered for prediction, of which 80% are masked, 10% are swapped with random words, and 10% are left unchanged. For affix prediction, we face a multi-label classification problem. For this, we either group together affixes into a fixed number of sets and predict the set as a class label. The other option is to predict the affix probability vector. We evaluate both of these approaches in our experiments. We pre-train KinyaBERT on about 2.5 gigabytes of Kinyarwanda text and compare it to 3 baseline models. One is a multilingual model called XLMR that is trained on a large text corpora that is made of multiple languages. The other 2 baselines are pre-trained on the same Kinyarwanda text using either byte pair encoding algorithm or using morphological analysis without using the 2-tier transformer encoder architecture. All models are configured in the base architecture, which is about between 100 and 110 million parameters, with KinyaBERT using the least number of parameters. All models except the multilingual one are pre-trained for 32,000 gradient updates with a batch size of 2,560 sequences in each batch. We evaluate the pre-trained models on 3 sets of tasks. One is the glue benchmark, which has been often used for evaluating the effectiveness of pre-trained language models. We obtain our glue benchmark data by translating the original benchmark data into Kinyarwanda using Google Translate. The second task is Kinyarwanda named entity recognition benchmark, which is a high-quality data set that was annotated by trained native speakers. The third one is a news categorization task, where we pull news articles from several websites and collecting their categorization tags that were assigned by the authors, and then essentially trying to predict the same categories. And now we go to the results. For the glue benchmark, we find that KinyaBERT consistently outperforms baseline models. Here we show the average performance for 10 fine-tuning runs. We also ran a user evaluation of the translations that are produced by Google Translate. Essentially, users rated about 6,000 examples, assigning scores on a scale from 1 to 4, assessing the quality of the translations. The result is that many translations were noisy, but all models had to cope with the same translation noise, and the relative performance between the models is still important to notice. For the named entity recognition task, we also find that KinyaBERT gives the best performance with the affix distribution regression variant performing best. These results are also averages of 10 fine-tuning runs. For the news categorization task, we find mixed results. Previous work on text classification for Kinyarwanda had found that simple keyword detection is mostly enough for solving this specific task. Therefore, there is less gain from using pre-trained language models on this particular task of news categorization. We also conducted an ablation study to see if there are alternative structures that improve performance. For the glue benchmark, we find that using affix sets consistently performs better, while affix probability regression objective yields the best performance on named entity recognition. Also, by looking at the loss curves for fine-tuning, we find that KinyaBERT has better convergence in most cases. So to conclude, this work has demonstrated the effectiveness of explicitly using morphological information in pre-trained language models. The proposed two-tier transformer encoder architecture enables capturing morphological compositionality, which is an important aspect of morphologically rich languages. These findings should motivate further research into morphology-aware pre-trained language models.